We got a lot to do here. So we're going to make this. I've already made it. I made an animation because that's what you're supposed to do. You're supposed to start off with, hey, look what we're going to make, and then make it. So that's what I did. So this is a potential barrier with a wave function moving that encounters the barrier and then tunnels through it. I mean, it's kind of cool. And I'll go ahead and say, there are a lot of examples of this online. But I wasn't really happy with them because a lot of them were written in the perspective of a programmer and the code wasn't as easy to understand. So I'm going to try my best to explain all the nits and bits and pieces of this code and to write it not in an elegant way, but in a simple way. And here we go. Okay, so I'm going to start off with some lectures on the physics behind this. I'm going to go quick. I've already talked about some of this stuff, so let's just get to it. So the most important thing is the one-dimensional Schrodinger equation. So this is the relationship, a differential equation for the wave function psi, which depends on both time and space. So we can assume that I could break this wave function into a space part, psi, lowercase psi, and a time part, f of t. Okay. If I do that, I'm going to skip a lot of the steps. If I do that, you can show that I get part of the equation only depends on time, and the other side of the equation only depends on space. And the only way that that's true, if you have a space part equal to a time part, then they both have to be equal to a constant. We call that constant E. And then if you solve for the time part, because it doesn't have a potential in there, assuming a time-independent potential, that's our solution for the time part of the Schrodinger equation. E to the negative I, et over h bar, where E is a constant energy. Great. Okay, and then we're left with the space part, and this is what we need to solve. The space part only depends on the lowercase psi, only depends on x, and the potential only depends on x. That's our assumption. We need to solve this. We can solve this in a lot of different ways, really 3 different ways at least, but most importantly, we can use the finite difference method. And this is kind of cool, but there's a one little jump part right there, and we're going to get into some crazy math that we're going to need Python to solve. So assume that you break this wave function into finite elements separated by a space delta x. Delta x, delta x, delta x. So I have psi 1 through psi 6. And I should have put that as psi 0. I can define derivatives in finite space as a finite difference. Right? I can define the derivative with respect to x as just the slope of these points. So here is 3 generic points. If I want to find the derivative of psi at point I can use the point after it, the point before it, and the width to 2 delta x, and I get the following expression. I'm flying through this super fast because there's programming stuff and more important things I want to do. So that's the first derivative, but we don't have the first derivative in our Schrodinger equation. We have the second derivative. So I can define the second derivative as the difference between the slope at the half interval points. So psi 1 I plus a half minus psi I minus half psi prime, which is the derivative, divided by the distance delta x. And then if I just use that for my derivative, the psi primes, I use the psi prime half. I can plug everything in. I get that, and I get this. This is the most important thing. This right here, that's my second derivative. Now, it's so important I put a box around it. Now I can go back to the Schrodinger equation. If I go back to the Schrodinger equation, which is this right here, I can replace that second derivative with a difference. So if I just put in my definition of the second derivative as a finite difference, I get that. I pulled the delta x squared out because it doesn't change. And I get those terms. And you'll notice I have an I plus 1 term, an I term, an I minus 1, another I term, and another I term. These are all psi's, right? So that's that. And then if I group them together in a logical way, I have 2 terms that are psi I plus 1, psi I minus 1. This is all psi I. And then over here I have E psi I. That's what I want. Now imagine that I only have 5 points, 0 through 4. And if I have boundary conditions on my wave function, which you would have in an infinite square well, and you don't have in a lot of other cases, but we'll force it on there. We're going to pick some point where we say it can't go past that. So I know I'm going to set psi 0 to 0 and psi 4 to 0. Those are set. If I do that, then I can write 3 equations for the following middle points, psi 1, psi 2, psi 3. So this is for psi 1. You'll notice it has a psi 0 term in there if I use my equation, but psi 0 is 0. So that's fine. And then I have a psi 1, and then I have a psi 2. And then I do the middle point, it's got psi 1, psi 2, psi 3. And then the last point, psi 2, psi 3, psi 4, which is also 0. But there's 3 unknowns in here. Psi 1, psi 2, psi 3. And it's a set of 3 linear equations. I can write that as the following matrix equation. So this, if I write this as my matrix, multiplied by the vector psi 1, psi 2, psi 3, it's going to be E psi 1, psi 2, psi 3. Now, just to make things simpler, I put this K as this thing over there. Otherwise, it just looks messy. And this is the same set of equations. If I take this row times that column, I get that equation. And notice here that psi 0 isn't in this equation, right? Because I don't have a psi 0 there, which is fine. It's fine. Because psi 0 is 0. Doesn't matter. Then I do it for this row, I get this equation. And so you can see I build these equations with that matrix. But now I have an eigenvalue problem. This says a matrix multiplied by this vector is equal to a scalar times that vector. That's the eigenvalue problem. That's the problem that we want to solve. And in fact, we could write this as the Hamiltonian H, which is that whole matrix thing, operated on psi is E psi. And that's what we're going to do. Okay. Now, we do have, let me just do a couple things. Number one, what are we going to start with? Oh, no, not that. I should have put this as an animation. I didn't. I apologize. I'm not going back now. It's too late. So I can find, from the eigenvalue problem, I find the psi ends. I find all my eigenstates, right? I know those solutions. Space only. It depends only on space because we're dealing with a space differential equation. And they all come with their own separate energy eigenvalues. If you do the infinite square well, we get these, and we know what they are analytically. If we do it another way, like we're going to do numerically, then we only have function. We just have data for these. I have data for psi n. I'll have numbers for en. I don't know what they are, and I don't care. But once I know what those wave functions are, I can use them to create other solutions. So I can find any other solution as a linear combination of these known solutions. And that's what this is right here. This is the wave function for anything could be represented as a sum of coefficient cn's times those wave functions psi n, and then I have to include this time part in here too, which has en in there too. So all the time parts are different. So we're going to get this superposition of states right here. Now, how do we find the cn's? Well, the cn's are defined as the integral of psi, the complex conjugate of times an initial wave function that doesn't have time as 0, dx. So if we integrate over this, we can find Cn. So if you do that for n equals 1, we get 1. We do that for n equals 2, we get C2, 3, and so forth. So we get all our Cn's, and I can go back up here and add up the Cn's times the known solutions to the wave functions, which are up here, and the time part, and I get a wave function. And then I can just let the whole thing evolve in space, and that's what we're going to do. Okay. So here are the details I'm going to start with. This is my initial wave function I'm going to start with because I want like a pulse, right, that moves to the side. So you'll notice something here. I have, this is like a Gaussian distribution. X, that's the initial position, x0 squared. Sigma is this the width of the distribution. And this is does not depend on time, but it is a complex number. We have e to the I p x plus x0. And p is the momentum. I'm going to use p as 40. And then this v0 is the height of the barrier. I'm going to use this as p squared over 2m, the kinetic energy of the barrier. And we can change this once we get things working and see what happens. But there we go. Okay, so I'm going to jump over to Python. And I'm going to set this up. I'm going to run through this, and we're going to get no errors. And I'm going to do it from scratch. And, I go back and forth. What's the best way to do this? And I'm not absolutely sure. Would it be better to just show you the code or a meme? No, I'm not going to show you a meme. That was for class. Let's just close that. There it is. Okay. And this is off a little bit. I don't know why. I want to make it good sized. Let's see. Okay. What was I saying? Oh, I don't know if it's better to, have the code already completed and then to see the pieces, or if I do live coding. I kind of enjoy live coding. I make mistakes sometimes, but, that's where we are. So let's just get into it. Hopefully you can follow along. I will post the code somewhere, and you can use it later. And I'm going to break this into cells because I like to think in cells. If you do it all in one code, it's a little bit easier to change. You don't have to rerun things. But let's just jump into it. So I'm going to need Numpy. Import Numpy as NP. Some people will say NumPy, and that's cool. I say this. Import matplotlib.pyplot as PLT. I think one of the things I like about doing it live is that it makes me go slower. It gives you time to think about what's going on. I could be wrong. Maybe you just want the answer. I don't know. I don't know what you want. I know what I want. I want to make this work. And it's fun, right? It's fun to make it work. It's fun to troubleshoot stuff. I'm going to start out with my constants. And let's see, I'm looking at my stuff. I have m equals 1, which is, we're going to use these fake units. We're not going to use the real mass. We're not going to use the real Planck's constant, h bar, any of that. We're just going to make it simple. You can change it later. M equals 1, h bar equals 1. Now, I want to make my, I have to make an infinite square well, because I have to have points where the psi is 0. I have to have real boundary conditions. But I want them bigger than what I want to actually look at. I don't want to bother about those boundary conditions, so I want it kind of big. Let's make this x min equal to -6, x max equals 6. Oh, I did 6.5. I'm not sure why. 0.5. Okay. Now I need to pick how many pieces I'm going to break this into. I feel like this is a little small. Let's make this a little bit bigger. I feel like, let's make this bigger. I can scooch the whole thing over, I think. Okay. And it doesn't matter how long this takes. We're spending time together. It's quality time, right? Okay, now I need to know how many pieces I need to break this into. I'm going to say n equals 1,000. One of the things you're going to notice is that, remember that my eigenvalue, my matrix Hamiltonian, has to be 2 by 2 less than this. So it should be 2 less than the number of pieces, but I'm actually going to plot 1,001 pieces. I'll show you. And if you don't know about that, that's fine. I got another video on that. I don't want to, there's so much stuff. So let's make our x values. X equals np.linspace, x min, x max, n plus 1. So what that's going to do is add 1 extra element to the end, and because I want 1,000 spaces, not 1,000 points, I will post, I have a Numpy cheat sheet at the end of this, and I'm going to go back to that Numpy cheat sheet. So you can remember all these things that don't always make sense. I'm going to need delta x, right? That's in there. And I could do it two different ways, but I'm just going to literally calculate delta x. x1 minus x0. That way I make sure I get the right thing. Is something not right? This is print out. Something doesn't look right. Yeah. You know what? That's what I had. Oh, boy. I had that as a... there we go. I had that as a markdown cell. I don't know how I got into that. Okay, so it's working. I thought something wasn't looking right. What else do I need? I need p. P equals 40. I need v0 equals p squared divided by 2 times m. I need sigma. That's for my initial thing. Sigma, I'm going to use 0.15. X0, where is it going to start? I'm going to start it at 2, right? I have my well going from negative 6.5 to 6.5. So I don't want to be near the walls. I don't want to interfere with the walls. Okay, now I need to make my my potential function. It's going to be 0 most of the place, but I want it to be the same length as my number of x values. So this is the trick that I use. You can do it different ways. I'm going to say v equals 0 times x. And then let's just show you print the length of v. 1001. So it made it 1001 things times x. So this is what's great about arrays in Numpy, is that I can do these kind of operations and I get another array back. And so now I already have all my zeros filled into my potential. I just need to change a few of them to v0 for that little bump in the middle. Let's do that. For I in range length of v, it doesn't matter, v or x are the same length. So what I want to do is say, if the x value of that I, I'm going to go through all the elements. If the x value is greater than something, then I'm going to change the potential. Let's say if xi is greater than, I'm going to put the bump right in the middle, 0, and xi is less than some value, let's say 0.5, that's going to be the width of my well. It's going to start at 0 and end at 0.5. If that's the case, then vi equals v0. Does that make sense? Okay, that should do it. Let's go ahead and plot this just so we can see what it looks like. plt.plot xv. And it didn't. Oh, it did like it. There it is. So there's my well. And it goes up to 800. Oh, that's fine. It's huge. Doesn't really matter. You know, we'll plot the potential just so we can see where the well, the barrier is, but we'll have to shrink it down to make it, you know, a good size. And we can do that later. That's not a big deal. Next, I want to make my wave function, my initial wave function. So now, I want this two less than the number of x values, because I don't want to put it for the first or the last one. So my x values are n plus 1, so this is going to be n minus 1 long. I'm going to copy this equation because I type it wrong all the time. I have it up here. I'm going to copy it and then I'll go over it, because I know this is exactly where I'd make a mistake. So here I'm calling this size 0, and it's e to the, is exactly that equation I showed you. E to the negative x 1 colon negative 1. 1 colon negative 1 says use x, but don't use the first value and don't use the last value, right? Because I want it 2 less than my x value, so I can't do x, or it'll give me the same length. Plus x0 squared divided by sigma squared times e to the ij. So ij is negative 1, is I. That's I. 1j is the square root of 1, negative 1. P, and then I have x, again, 1 to negative 1, plus x0. And that's my initial wave function. Okay, let's normalize this. See, I got to get... Okay, let's normalize this. So to normalize this, I'm going to say that I'm going to call this A equals np.sum. That just adds up whatever I put in there. And I want to sum np.abs size 0, spell it right, squared dx. Remember, to normalize, we're saying the integral of psi star psi over all space is 0. And I really should do this as the complex conjugate of psi times psi, but this works too. I guess it works. I'm not sure if it does. Well, that's what I did before, so I'm pretty sure it's the same. And I'm going to assign that to my value a. So that is my integral. And I want it to be 1. So one way to make it 1 is to go back to my psi 0 and divide by every term by the square root of a. So let's do that. Psi 0 equals psi 0 divided by np dot square root a. And now let's plot it. plt.plot. I don't want to plot this potential because it just makes it more messy. And I don't want to plot it on x. I need to do x 1 to -1, psi 0. And there's an error. Oh, because it's complex. So I need np.abs for the absolute value of that. And there's still an error, and I left off a thing. Okay, got it. So there's my normalized wave function. It looks good. You look good. We all look good. We're ready to move on. Okay, let's now make our eigen value, our matrix of Hamiltonian, so we can find the eigenvalues. So this, I'm gonna write it the simple way. Okay, let's just say temporarily n equals 6, just so you can see how it works. And I'll have a cheat sheet on this later. I don't want to spend too much time. So I want to do a 6x6 matrix. I'm going to show you how to do that. H equals np.diag makes a diagonal matrix, and I want to fill it with np.1s. And how many do I want? n. And then let's print that. So see, if I make it 6, I can print it. So there's my diagonal matrix, and then I can multiply that by -2 or whatever. And now what if I want an off-diagonal matrix? Because remember, I had that tri-diagonal matrix. I can add a diagonal on there. Let's say plus 3. I'm just making up stuff. Plus 3 np.diag, np.1s. Oh, technically, we're going to put this as n minus 1, remember? Because we want, if we have 1,001 points, we want 999 by 999 matrix. But I'm just going to leave it as n. But this one is going to be one less than that, because this diagonal here has one fewer than that diagonal there. And then I'm going to put the comma 1 that says move up. And if I print it now, you see it filled in right there. Okay, so I have the matrix. It has a bunch of constants in there and stuff. So I'm going to go up here and copy that just so we can make sure that I don't make a mistake. And that's that. Okay, so there's my matrix. Let's just print h.shape and see if it's the right size and see if things work. So it's 999 by 999, and that's what I wanted. It works fine, so good. Now I'm going to find the eigenvalues and the eigenvectors, and I'm going to use the Numpy linear algebra eigenvalue function. E psi, it's going to return both of those, the eigenvalues E and the eigenvectors psi. It's np.linearalgebra, linearalg.eigh, and this is going to be on the cheat sheet because you can't remember this, and I'm going to give it the matrix H, and that will return those values. Now, it returns the energy values fine. They're just a list of numbers. The eigenvectors are actually wrong, right? It's going to return them in columns, and I want them in rows. So I'm going to need to transpose that vector, that matrix. Psi equals psi dot t will transpose the whole thing. Now I need to normalize all those. So we're going to do the same thing. A equals mp dot sum. Psi, I guess I should do psi. This could be imaginary. No, it won't. That's fine. mp.abs psi 0, the first one, squared times dx. That's going to be the integral over all space. And then I just need to divide by that. Psi equals psi divided by mp dot square root of a. And remember, psi is all of the solutions. So I only normalized the first one, but I'm going to use that same normalization for all of them. And I'm pretty sure that works. Let's just plot a couple of these solutions. plt.plot x 1 to -1. Remember, we have two fewer. Psi 0. Let's do psi 0, psi 1, and 2. What the heck? Stop. Okay, so there's my solutions. Psi 0, psi 1, and psi 2. That's kind of cool because we've got that little bump there. You notice that this one is this one's only on that side. This one's on that side. It's kind of cool. Okay. What do we need to do next? Now we need to find the C coefficients. And you'll notice I'm breaking it into cells again. That's fine. For I in range length of V No, that's just to plot V. I'm sorry. Let's plot V. I'm going to plot V. This is going to... Oh, no, I'm going to do that later. Okay, because I'm going to... Let's just plot. Let's do this the simple way. The simple animation, and then I'll do it the complicated animation. I'm going to plot V, but I'm going to multiply it by some constant. plt.plot x... Oh, that has all the x values, right? X 0.003 times V. Let's see if that works. Yep. Okay, that's good. Now I want to find the C coefficients. I first need to, I'm gonna find all these elements, but I need to first set them equal to something. And I want to set them equal to something. They can be zeros, but I want to make them all complex numbers. So to do that, I'm going to use a trick. C equals 0 times psi 0. Remember, psi 0 was a complex number. So if I multiply 0 times that, I still get a complex number. So I have a list, I have an array of complex numbers that I can then go ahead and change those. If you don't do this, you can't do the next step. And there's, like I said, there's other ways to make that list. For I in range, the length of C, do the following. Ci, the ith element, is going to be equal to np.sum psi np. Let's do np.conj, the complex conjugate of psi I times np dot, no, I don't have to do that, psi 0 times dx. That's that integral, right? That's Cn equals the integral of psi n star psi 0 dx. I just did it. I found it. I found all my Cn's right there. That was it. Let's just print out a couple of those C's just to see if it works. Print C0. Let's just do C1, C2. Okay, so we're getting, and they are complex numbers, so that's fine. Whew, okay, now we are ready to rock and roll. We know our size 0. We know our size. I can calculate psi x at any time because I know my energies and I know the whole wave function. So let's just pick psi and let's plot psi at different times. Let's just do it for t equals 0 and make sure that works. I don't want to print these anymore. So now I need to calculate psi x of t. So I need t equals 0. I'm going to need dt 0.0. I use 0.001, and we'll get to that later. And I need to calculate psi. So I need to go through all my c's and add it up to psi. So, but before I do that, I need to set psi equal to 0 so I can add it to something that's 0. So psi equals 0 times psi 0. All right, so that'll just set it all 0. And if they're complex, they're complex, and it's all fine. Everything's good. I think that's fine. For I in range length of C, I'm going to go through and add up my C values, which I know. Psi equals psi plus Ci times psi I times the time part, which is np.exp negative I, which is ij, times t times, or ei times t divided by h bar. I think that's right. Yeah, I didn't put the h bar in there. Am I there? That's fine. So that's going to calculate my psi. Let's go ahead and plot that. plt.plot x, not all of them. Can you see with this? Sometimes I get out of the... I wasn't paying attention. I was just excited. Oh, again, it's imaginary, so I need to say np.abs and plot the magnitude of that. There you go. So there's my potential. It's a little big. And there's my wave function at time t equals 0. So I can just do it again. Let's do it again, 5 delta t later. And I could also plot the real and the imaginary stuff too if I wanted to. Let's do that. Let's do PLT. No, I don't want to do that. I'll do that later. So I can do this. PLT.show. And then I'm going to do t equals t plus 5 times dt. And then I'm going to do the whole thing again. So I need to recalculate psi. So I'm going to copy this whole thing and paste it. And I'm going to make another graph. Again, I'm having problems. If I move this, let's see. That's what I'm doing. Okay. And you'll see there's my t equals 0. There's the next time. I didn't plot the potential. I should have plotted the potential. But there it moved a little bit, not too much. Let's change that to 15 delta t. And so it's moving. Okay. Now let's do another one. And let's do it at just something later. And I'm just showing you this because this is the easy way to do this, right? Making multiple graphs, because animations can be hard. So there it is. It's hitting the boundary. Some of it's reflecting and something's passing through, and that's exactly what I wanted. Okay, but you don't want that. You want to make an animation. So let's make an animation. So I'm going to delete that stuff. Up to here. Animated graphs in Python are not easy for me, but I find them easier in web VPython. So if you have VPython installed, then you can make animated graphs the VPython way. So I'm going to do that up here. Let's just add a cell above this. From VPython, if you are doing Google Colab, not going to work. If you are doing Anaconda, not going to work unless you install. You're going to have to go install VPython. https vpython.org. That's where you need to go. So from VPython, I don't need everything. I just need a couple of things. I'm going to need rate, G-curve, graph, canvas, and maybe there's one other thing. Color. I don't need color, but I want color. Color. Canvas, I think I got it. Okay, so I'm going to import those things in here. And it didn't like that. From VPython, import. Import. Got it. Okay, so now I can use those. You could import the whole VPython module if you want, but I only need some of them. Now, in Python, I'm not going to plot this. I am going to plot the potential. But the first thing I need to do is set up all my graphs. So to set up my graphs in VPython, I need to do, I'm looking at my notes here just to make sure I don't make a mistake, because I'm getting very close. One of the things that's really different, you have to do this. You have to do scene equals canvas like that. You have to do that. Otherwise, it doesn't know where to put the graph. Okay. Now I'm going to make a graph. G1 equals graph. X title equals X. Right. Y title equals, I'm just going to call this stuff because it's not necessarily true. Width equals 500. Height equals 250. That's that. Now I'm going to add some stuff in there too. And now I'm going to need some things to plot. F1 equals G curve. Color equals color.blue. And blue is color is a built-in function to VPython, so I imported that. Let's call this FV for the potential. G curve color equals color.red. And then I can plot real and imaginary stuff. I'm not going to do that. It's not too hard. I showed you in the animation, but I'm not going to do that today. Okay. So let's go ahead and plot the potential. For I in range length of v. Remember, because it's an array, so I need to go through that array and plot v versus x. fv.plot xi, and then I'm going to say 0.003 times vi. And let's run that and see if it works, right? Because hopefully our graph will work. There, it worked. Yay! You never know when things are going to work when they're not. So you just got to be excited when you can. Okay, now I'm going to make a loop over time. So I am going to say while t, I don't want it to be, you don't need this very long. And playing around with what time works the best can take some getting used to. So let's say while t is less than 0.5, oh, stay on page, 0.5, rate 20. And so I played around this already know. So rate is a VPython function that tells the animation how many loops per second. So this says do 20 animations per second. That's what it is. You can change it to make it run faster or slower. You do whatever you need to do. Now this stuff I need to put in my loop, in my loop, in my loop. Now also in my loop I need to have, to make an animated graph, I need an empty list and add stuff to my list. So I'm going to call that fdata. Fdata equals fdata. No, it just equals an empty list. Now, after I've calculated my psi, I'm going to go through and add all my x's and psi's, absolute value of psi, to my data list. Fdata equals fdata plus xi, that's my x value, and then my other one is going to be np.abs psi I. So that adds that point to the list. I'm making sure I did that right. Yep. Now, once I've got that, I am going to, I want to put this up here. Once I've gone through, now I can plot the whole thing and it'll make it look animated. Oh, this has got to be in. For I, that one calculated. Oh, I think I can do this. I think I can put it in here. No, I don't want to do that. I think you could, but I don't want to do that. So for I in range length of psi. And maybe it's not efficient, but it's safe, right? And safe is better than efficient. Now I can plot it. f1.data equals fdata. Now I need to increase my time. T equals t plus dt. And let's see if this works. I don't want to run it because I'm kind of scared. Oh, it did work. Check that out. So now you can take this. You can change the energy of the pulse. You could change the height of the bear. You could change the width of the bear. Notice here that it's interfering with the boundary walls, which I put in there. I don't really want that, but that's there. But this is a win. Now you also notice the graph is shaking around a little bit because it's auto scaling. You can fix that. It's not a big deal. But we won. We won. 38 minutes is maybe one of my longer videos, but we got it to work. We did a tunneling. I'm going to run it again because I liked it so much. Look at that. Love it. And so you could also plot the real and imaginary parts of the wave function. This is not the probability density. This is the absolute value of psi. But there you go. Hope you like that. And I told you I'm going to post this code somewhere. I'm going to post it to GitHub or whatever, and I'll put a link down below. If you made it to the end, you know you got to give yourself a double high five. Good job. I'm really good job myself because you know I make mistakes all the time. I'm pretty happy with this. Okay, I'll talk to you later.